Students, today we are going to learn about complex numbers rotation theorem. It is CONI'S method. Now, the prerequisite for this portion is your concept of understanding modulus and argument form of complex numbers. Apart from it, it would be required that you should have thorough knowledge of Z1 into Z2, what it leads to, in terms of modulus and in terms of argument. Apart from it, you also have to understand that Z1 by Z2 leads to what? That is mod Z1 by mod Z2 and argument gets subtracted. That is argument Z1 minus argument Z2. So these are the prerequisites. Apart from it, complex numbers part 1 you have already done, and that I am presuming. So we come to CONI'S section rotation method. So CONI'S section rotation method, this is the expression which we will be arriving at. This would be the last thing which we'll be arriving at while deriving the CONI'S rotation method. And when it is all about rotation, we have to understand that complex numbers can be treated as vectors. When they are treated as vectors, rotation of a vector you have already understood even in vectors chapter. So we go for the basics here. Now this is the final figure. I'll come to this little later, but before that I have basically divided the whole rotation theorem into two parts. One, I will consider that Z1 and Z2 be the position vectors. These are the complex numbers which are position vectors of points Z1 and Z2. Okay? Now we consider Z1 as modulus Z1, that is the length of this line segment, yes, and E iota phi. So this is Euler's representation of complex number. Isn't that so, students? Now, this complex number Z2 would then be mod Z2 E iota theta. Am I right, students? Because the angle which it makes with the positive direction of x-axis is theta. Now, what is the situation here? That Z1 vector is there about which we know. Okay? Z2 is something which we are supposed to come at. This we don't know, although we have expressed it like this. But at the same time, here what we want to do is that the length of Z1 is obviously mod Z1 and mod of Z2 is known. Come again, sir, you have made us confused. Just once again. Z1 is completely known to us. Okay, students? Z2 only modulus is known. This theta is not known. What other thing is known? That is alpha. That is how much angle it is making in the positive direction of in the anti-clockwise direction with Z1 vector. I hope you understand, students. Now, what I am trying to do is that this Z1 vector, I am trying to rotate it by an angle of alpha in anti-clockwise direction. Okay, students. Now, given that this complex number we know, given that this modulus we know, can we arrive at actual Z2? That this theta is not known while this alpha is known. So I hope you remember the concept of argument Z2 upon Z1. Do you remember this, students? This I have earlier spoken it also, that you will have to have the basic understanding of argument of Z2 by Z1 and argument of Z2 by Z2 into Z1. Now argument, if you correctly remember, argument has to be considered either principal argument or argument. Here we are considering principal argument. Principal argument is something which lies between 0, which is inclusive, and pi, which is not inclusive. So what did I say, students? Argument here, which I am referring to the principal argument, which can also be referred to as an amplitude. Argument of Z, if it lies between pi and 0, would actually mean principal argument. Okay? So what is spelling I have used of principal? Don't make the mistake of writing PLE, principal value, principal value. Okay? That's the spelling you'll have to use. So if it lies between 0 and 5, you can call the amplitude or the principal argument. Now, argument Z2 by Z1, if you correctly remember, it is argument of Z2 minus argument of Z1. Sir, we cannot remember anything. What you are talking all about? Students, have you forgotten that Z1 or Z2, the complex number can be expressed in Euler's form? So if instead of Z2 I write R2, which expresses its modulus, E iota, here I have assumed theta upon R1, which is the modulus of Z1. I haven't expressed here, I'll express it here. And E iota phi. Am I right, students? So when you are talking about argument, this modulus doesn't make any sense here. What ultimately you are going to get? You are going to get argument. Since the bases are same, the powers will get subtracted. Isn't that right, students? So the argument of this complex number happens to be theta minus phi. And what is theta minus phi, students? Isn't that alpha? You can see yourself here in the diagram. This is theta, this is phi. So if I take the difference, that is alpha. Now here in our case, this alpha is given, this phi is given, this theta is not known. Obviously theta can be alpha plus phi, doesn't matter. But let's see how Z2 expression can be obtained, because only modulus is given, alpha is given, and these things are given. Okay? Now, having written this, if I write the expression here, I'll take up this color, Z2 by Z1. Okay? If you consider the complex number Z2 by Z1. Now, if we go to the Cartesian concept of complex number, when two complex numbers are divided and you obtain a complex number, you actually equate both sides, the real part and the imaginary part. Isn't that right? Two things you equate. While if you are expressing it in modulus argument form, then both sides modulus should be equal and both sides argument should be equal. Isn't that right? So Z2 by Z1 would be modulus of Z2 upon modulus of Z1 and modulus of Z2 modulus of Z1, and that is E iota, that is, this one is theta minus phi. Isn't that right? Achha. So I think this is not so clear. I'll make use of a different pen, a darker pen, perhaps. So if we have Z2 by Z1, correct, students? This is equal to, what is this equal to? This is equal to mod Z2 upon mod Z1. That is the modulus which it is equal to, and E iota, whatever is the argument of Z2 by Z1. Here we have learned argument of Z2 by Z1 is alpha. So instead of writing theta minus phi, I can write alpha. Now let's see here in this expression. We know what is mod Z1. Didn't I tell you that we have been given? Mod of Z2 is also incidentally given. Alpha is also given. You need not to find phi or theta separately. Theta is obviously not given, while Z1 is also given. So these all the things are given. You can convert or you can express this in terms of Z. You know, Z2 would be equal to Z1, then modulus Z2 upon modulus Z1 E iota alpha. And here you obtain the baby form of CONI'S notation method. That is, the complex number, if they are rotating about the origin, that's how it is happening. Okay, students? So this is one expression which I would really want to come up with before coming to the bigger expression. What is that? This one. Now let's talk about that. Here, if you can see in this diagram, I've already made this diagram, that Z1 is not the position vector of the complex number Z1, while it ends up, the tail is A, that is complex number Z3, and Z2 tail is also Z3. Now, I'm rotating this vector, which vector? AB vector, by theta angle, or let's call it as alpha, you know? Why don't we call it as alpha? That will make everything, alpha here also we took. Now here, instead of the tail as origin, we are having Z3 as the tail. Now, the rotation of Z1, this is known, given, this is given, this length is given. Okay, students? That means the modulus of this vector is given. Okay, students? Now, what is Z2 is my question. And that's what CONI'S rotation method answers. So let's see. Now, can I change this point with the position vector Z1 minus Z3? That means shifting the origin. Isn't that right, students? Instead of Z3, I make origin as the tail. But to convert it into like this, what I'll have to do? I'll have to shift it into a form wherein I'll have, excuse me, why don't I take another page? Yeah, that's a better option. So we have a new page. Now, look here. You have this as the real axis, students. This as the imaginary axis. Y-axis is the imaginary axis. And here you have this complex number, this one. And this head would be now termed as Z1 minus Z3. Am I right, students? I think this is slightly not clear. I'll make it clear. Z1 minus Z3. That means the head has been converted into, the shifting of origin has taken place. And here the other complex number would be Z2 minus Z3. Am I right, students? So the tail vanishes and it takes the form of origin. Okay? Now, again, this question now reduces to that this complex number which is given, which if you can compare it with the previous case of CONI'S rotation method, this is the complex number which you want to find out, whose length incidentally, and the angle by which you want to rotate also Yes, students? I take this color as well as, okay. Yes, students, this angle is alpha. So now, following the method which we did previously, okay, what did we do previously? Here we had Z2, here we had Z1, and here we have alpha. So instead of writing Z2 as Z2, we write Z2 minus Z3 as Z2. So we'll have the CONI'S rotation method applied here with Z2 minus Z3 upon Z1 minus Z3, and that would be equal to the modulus of the numerator, which we have discussed that it is given to us, and Z1 minus Z3. Am I right, students? and the argument would be the difference of the argument of the numerator and denominator complex numbers, that is E iota alpha. Isn't that right, students? So to calculate the value of Z2, which is ultimately not known, we'll write Z2 is equal to this cross multiply, and Z3 I'll send it there. So Z3 plus Z1 minus Z3, and you have Z2 minus Z3 modulus upon Z1 minus Z3 modulus E iota alpha. Isn't that right? And let's see whether the same expression I had written earlier or not. So this is the expression which we were looking forward to, and this is the same expression. Z2, Z3, Z1 minus Z3, and this in this way. You know? So this is what we have obtained as CONI'S rotation method expression. Okay, students? Now we come to a very simple question. In fact, it's a fundamental question of rotation method. Okay? So we'll do that first. And before going to that question, we should do certain note points as well. Number one, suppose you want to rotate a vector, I mean the complex number, by 90 degree in anti-clockwise direction. How do you handle that? I mean, that's simple. Suppose this is a complex number Z1. Okay? This is a complex number Z1, and the tail is at origin, let's say 00. I mean, real part 0, imaginary part 0. And you want to rotate this guy Z1 by 90 degree without changing the modulus. Okay, students? Let's put this condition as well. So we'll have okay, they aren't allowing me to make use of other colors. So 90 degree we have to rotate it. Okay, this is the complex number Z2 which we want to reach. This is 90 degree, and I don't know what this Z2 is. Now, what we'll do, we have Z2 by Z1. We'll make use of the first CONI'S rotation method rule which we used, is equal to mod Z2 by mod Z1, which incidentally, since mod Z1 and mod Z2 are equal, so they will cancel and give you 1, into E iota, the angle between the two vectors. The angle between the two vectors is 90. So instead of alpha, here now I am writing E iota pi by 2. Now just tell me, what is E iota pi by 2? Can you help me? Yes, students. E iota pi by 2, that is the cis form of complex number. This is cos pi by 2 plus iota sine pi by 2. Okay? Cos pi by 2 would be 0, isn't that right? Sine pi by 2 is 1. So this boils down to iota. So instead of E iota pi by 2, I can write iota. So what Z2 comes out as? Z2 is iota Z1. So that means if we multiply a complex number by iota, it gets rotated by 90 degree in anti-clockwise direction. Wow, what a concept we have learned. Come again, once more. If a complex number is multiplied by iota, it gets rotated by 90 degree in anti-clockwise direction. Okay? So this is Z2 iota Z. Now I can relate a very important and good question which has been asked previously in IIT JEE, and that was the year 2005. Okay? So I'll just show you that question. That question was that there was a complex number Z, there was a complex number iota Z, there was a complex number Z plus iota Z. Okay? These three complex numbers were there, and it was being asked that if they are the vertices of a triangle, then what is the area of the triangle? That means if I consider it as A vertex, this as B vertex, this as C vertex, nothing else was given. If you consider these as the vertices of a triangle, then what is the area of the triangle ABC? The triangle area ABC can be written in this format. This is a format generally we use in RMO, Regional Mathematics Olympiads. So let's draw this.